Hello, everyone. Welcome to another UKSPA seminar. Today, we have Anna Salagean, who is a senior lecturer in the Department of Computer Science at Loughborough University. She previously held positions at Nottingham Trent University, University of Bristol, and the University of Bucharest in Romania. She obtained her PhD from the University of Linz, Austria. Her current research interests are mainly in cryptography. Specifically, she studies the mathematical properties and the constructions of cryptographic Boolean functions and the cryptographic sequences that are used in the design of symmetric key ciphers. She also worked in the area of algebraic error correction code. Today, she will talk about estimating the nonlinearity of cryptographic Boolean functions. Now let the speaker speak.
Thank you, Changyu, for the introduction. And also thank you, Changyu and Sia, for organizing this series of seminars. My name is Anna Salagean. And this work is joint work with Pante Stanica. It was first presented about a year ago at the SETA conference. And very recently, the full version was published in the journal Cryptography and Communications. I will start by discussing how Boolean functions are used in cryptography, and in particular, what we mean by nonlinearity. Then we will discuss some linearity tests and affinity tests and present some new bounds that we have proved. Based on these bounds, we will present the method that we devised for estimating the nonlinearity. Now, Boolean functions are used in many areas in computer science. Here, we are interested in their use in cryptography. They are used, firstly, in the design of symmetric ciphers. For example, in AES, a block cipher, which is very widely used today, the most widely used cipher, one of the several operations that are done in AES is a byte substitution. And the byte substitution uses an Sbox. So you've probably seen this Sbox before. It's convenient to write it as a table in hexadecimal. So what this table means is that we have a function that we apply for this substitution. And if, for example, the input is 1e in hexadecimal, the output is 72, again, in hexadecimal, in hex. Another place where Boolean functions are used in cryptography is in the design of stream ciphers. So we have what's called a filtering function for some constructions of stream ciphers. And I will show you a part of the specification of the cipher grain. So in grain, we have an LFSR, linear feedback shift register, and a nonlinear feedback shift register. So these are clocked, and at each clock step, the contents of some of the registers, so 5 of these registers altogether, are used as an input to a function. So this function is called the filtering function, and the output of that function is 1 bit, and the output becomes the key stream bit for the stream cipher. Moreover, we can also look at the whole cipher as a Boolean function and analyze it as a Boolean function. If we are dealing with a block cipher, the input of the function would be a block of plain text and a key. and the output is a block of ciphertext. If we're dealing with a stream cipher, the input is the key and an initialization vector, and the output is a bit of the key stream. Throughout this talk, f will be a Boolean function with n bits input and 1 bit output. We are all familiar with propositional logic, where we have two truth values, true and false, which are often represented as 1 and 0. And we have Boolean operations such that and, or, and not. For cryptography, we use a different approach quite often. The 0 and 1 this time are viewed as the two elements of the finite field of integers modulo 2. And the operations are addition and multiplication modulo 2. So note that addition is the same as exclusive or, and multiplication is the same as and. To check that indeed this algebraic approach lets us express the same kind of things that we had in propositional logic, we can have a look at the Boolean operations and convince ourselves that they can indeed be expressed in our algebraic setting. So for example, non-A equals A plus 1, A and B is A times B, A or B is A plus B plus AB. So just to stress again, the operations here are addition modulo 2 and multiplication modulo 2. Now for expressions in propositional logic, we usually use the conjunctive normal form or the disjunctive normal form. In our algebraic setting, we will use what's called the algebraic normal form. So this is an example of algebraic normal form. We have this function in 5 variables, x1 to x5, and it is expressed as a sum of terms, sum again modulo 2, and each of the terms is a product of terms. So algebraic normal form means that the function is represented as a polynomial, and each variable appears with degree at most 1. Why is it sufficient to have all variables to degree at most 1? Well, if you think that these variables will represent 0 and 1, if you square 0 or square 1, the result is the same as the original value. So there's no point in squaring a variable in this context. And the nice result is that any function can be represented in algebraic normal form in a unique way. Once we have the algebraic normal form, we can talk about the degree of the function. So for example, this particular function here has degree 4. So we can see here this term has the highest degree among those terms, and it has degree 4. If a function has degree 1, we call it an affine function, and we'll denote by A the set of affine functions. So an affine function will be sum of variables. So for example, x1 plus x2 plus x5 plus 1, that will be an affine function. If an affine function has the constant term equal to 0, so has no constant term, then we call that function a linear function.
Anna,
yes.
There is a question in the chat from
yes.
Roberto, and the question is, can they have their negations, like not x1 multiply
no.
x2, x3?
Oh, okay, I understand the question. Now we are not using not. We got rid of those operations. So if we were to use not, we are using this algebraic operation. So I understand that for, say, conjunctive normal form or disjunctive normal form, we use not. Here we are not using not. It's enough to use addition and multiplication, and these identities here show us that it is indeed enough.
Yeah, thank you.
Okay. Is there? Okay, thank you. Yes. So please do feel free to ask questions at any point. All right. So an affine function is something like x1 plus x3 plus x5 plus 1. Linear function is the same sort of thing, but we are not allowed to have plus 1 at the end. All right. Now, for cryptographic applications, when we use Boolean functions in cryptographic applications, we do not want to use any affine functions. So it's very important that the function should not be affine. Now, why is that? If we use affine functions, there's a number of attacks that can be mounted against our symmetric cryptography cipher. So there's linear cryptanalysis, differential cryptanalysis. They exploit the fact that the function is affine. From an intuitive point of view, you can think that a linear system of equations is very easy to solve using a normal linear algebra. Also, an affine function can easily be interpolated. The composition of affine function is still affine. So it opens the way to lots of attacks. So what we need to remember is affine is bad for cryptography. Also, if a function is close to being affine, that's also bad. The attacks also work for functions which are almost affine. Now, what do we mean by close to being affine? We will need a metric, so a distance. What we use as a distance. The usual distance used in this context is the Hamming distance. So the Hamming distance between two functions is the number of inputs on which the two functions are different. And here we will use the normalized version of the Hamming distance. So the distance between two functions f and g is obtained by counting for how many inputs f and g give different results, and divide that by the total number of inputs, which is 2 to the power n, if we have n variables, and each variable can be a 0 or a 1. Note that this distance also can be viewed as the probability of the two functions to be different. Okay, so if the two functions are the same a lot of the time, then the distance between them is small. So it makes sense that they are almost the same if their results are the same almost all the time. All right, so that's the motivation for this definition of the distance. Since we have distance from between two functions, we can also define the distance from a function to a set of functions. So the distance from a function f to a set of function s is the distance from f to the closest function in that set. Now we are ready to define the nonlinearity. So the nonlinearity of f is the distance from f to the set of affine functions. In other words, the nonlinearity of f is the distance from F to its best affine approximation. So if we think what affine function coincide with this function as often as possible, and then see what the distance is to that function, that is the measure which we called nonlinearity. All right. Now, as I said, we don't want our cryptographic functions to be close to being linear. So in other words, now that we have the notion of nonlinearity, our requirement is that we want high nonlinearity. So the functions should not be close in this sense to a affine function. This is not the only requirement that we have in cryptography. There are other parameters, which I will not go into detail here, but we do want good values for some other parameters as well. Now, what values can we have for the nonlinearity? What's the range that nonlinearity can take? It can start from 0, because obviously an affine function has nonlinearity 0. It's a distance 0 from the center of affine functions. And then at the other extreme, the highest nonlinearity that we can have was proven to be just under 1/2. So it has this expression where n is the number of variables. So 1/2 multiplied by 1 minus 1/2 to the power n/2. This upper bound can be achieved, and the functions which do achieve that bound are called bent functions. There are many known constructions of bent functions, and this area of research is an ongoing area. So it might look at first sight that we should always use bent functions for cryptography because they have the maximum possible nonlinearity. Now, this is not quite the case because we have to optimize a few other parameters. So although bent functions are optimal for nonlinearity, they might not be optimal for some other parameters. So we don't always use bent functions. If we go back, for example, to the specification of the grain cipher, so this nonlinear, this function here, the filtering function, there is a specification of the function. So it's here, as you can see, it is given in algebraic normal form in the original specification. And also there's an explanation of how it was chosen. So it has to be balanced, correlation immune of the first order, and algebraic degree 3. Nonlinearity is 12. Well, this is the non-normalized version. If we normalize it, it's 12/32, so it's 3/8 for this particular function. All right. So we want the functions that we use in cryptography, we want them to have high nonlinearity. We can't always use bent functions, but even if they're not bent, they should be close to this high nonlinearity. There's also an interesting result which shows that most Boolean functions have a high nonlinearity. But it's still important to avoid the ones of low nonlinearity. Okay, so that's the definition of nonlinearity. How would we compute nonlinearity? So let's look at an example. Let's say this function f in 3 variables. This is the algebraic normal form of the function. And we can then compute a truth table for the function. Truth table, as usual, as we are used with in logic. And then we can compute the distance between this function and affine functions. So for example, let's consider the affine function x3. So that is an affine function. It's actually a linear function. And see how often is our function f different from x3. So here it's different. There's one difference. Here's the same. There's a second difference here. And the third difference here. So for 3 possible inputs, the functions are different. And there's 8 inputs altogether. So the distance between the 2 functions, the normalized distance, is 3/8. We can then compute the distance from f to some other affine functions, x1, x2, x1 plus 1, x2 plus 1, and so on, and see which one gives the smallest result. And for this example, it is actually x1 plus x2, which is at smallest distance of f. If we look at the truth table of x1 plus x2 and the truth table of f, we will see that they are the same almost always. There's only one difference here. So the distance is 1/8. So only one difference out of the 8 possible values. So this is the closest, and therefore this is the nonlinearity of f. It's 1/8. So to compute the nonlinearity of f, the naive approach would be to just compute the distance to all the 2 to the power n plus 1 affine functions by using the truth tables. And this gives of 2 to the power 2n algorithm. We can do a bit better. We can compute what's called the Walsh-Hadamard transform, which is a type of Fourier transform. I will not go into details, but we can start with a truth table and apply an algorithm similar to the fast Fourier transform. And that will give the Walsh-Hadamard transform and the nonlinearity in big O of n to the power n2 to the n steps. So it is better than what we had before. Still, what can we do when n is very large? So for example, is if n equals 80, so a function in 80 variables. What should we do with that? 2 power 80 steps of the algorithm is quite high. Actually, we're already in trouble if we want to write the truth table of a function in 80 variables. So that would have 2 to the power 80 bits. So we already have trouble storing and processing this sort of functions. So for some functions in many variables, we can compute the nonlinearity in an indirect way. So for example, this function x1, x2 plus x3, x4 plus and so on. It is known that this function has nonlinearity equal to this value here, which, if you remember, is the maximum possible nonlinearity. So this function is a bent function. This function here, which consists of just one term, we can compute the nonlinearity for that one without computing the whole truth table. And the nonlinearity is quite small, is 1/2 to the power t. So there are a few functions for which we can compute the nonlinearity. But for most functions, it's not possible. So let's look at another example of a much more complex function. So let's look at the whole cipher and express it as a function. So I will use the stream cipher Trivium. Just a quick look at the specification of Trivium. it has 3 nonlinear feedback shift registers. So it has altogether a state of 288 bits. It's convenient for it to be written in a circle like that. And at each clock cycle, all the bits are shifted to the right, except for some specific bits which are computed according to this AND gate and XOR gates. And finally, some of the bits are XORed to output the key stream. So even if you haven't seen stream ciphers before, we can express this as a function as follows. So the inputs are 80 bits of initialization vector and 80 bits of a secret key. And the output will be the first key stream bit generated by Trivium. So stream ciphers can be thought of as pseudorandom bit generators. So they get this seed, the key and the initialization vector can be viewed as a seed, and then they start generating pseudorandom bits. And let's look at the first bit that is generated. The operation of the stream cipher can be expressed as a composition of functions. So we have this function h, which has 288 bits input and the same number of outputs. You can think of it also as a transition function if you are used to automata. You can think of it as a transition function. So these bits are updated. Most of them are updated just by being moved along one step. So bit I minus 1 is moved into the position I. So all the bits are moving to the right, as it were, for one step, except for these 3 bits. And these 3 bits are updated by this formula. So as you can see, the formula are not too complicated, and they have algebraic degree 2. And finally, some of the after this function is iterated 1152 times, then certain bits in the state are added together, modulo 2, and the result is the pseudorandom bit that Trivium generates. So what should we do with a function like that if we want to compute the nonlinearity? Well, the function h in itself is not too complicated, and we could compute the nonlinearity of each component. So the nonlinearity of something like that is 1/4, 1/4. But once we start iterating this function, the result gets more and more complex, and we can no longer compute the nonlinearity of the whole function. We also cannot compute the truth table of this function. As you can see, this is a function of 160 variables. Even if we keep the initialization vector fixed and only the key as variables, it's still a function in 80 variables. So we can't compute the nonlinearity of a function like that. In some situation, actually, the function might even be given as a black box function. So that means, just to remind you what the black box means, we can give some inputs to the function, to the black box function, and the function will return the output, but we don't know how the output is computed. So we can just query the black box, give it inputs, and it will give us the output, but nothing else. So how can we compute the linearity in such cases? If the number of variables is high, we can't compute it. If we can't compute it, can we maybe just estimate it? So this is the goal of this research, to find methods of estimating the nonlinearity when it is impossible to compute it precisely. And to this end, what we will do is use what's called a probabilistic linearity test or probabilistic affinity test. So I will next explain what I mean by probabilistic tests in this context, and then we will get back to our method of estimating nonlinearity. Okay, so a linear function, remember, a linear function is a function of degree 1 and without any constant term. So something like x1 plus x5 plus x7, something like that. It's not hard to see that a linear function satisfies this sort of relation. So if we take an n-bit input u1 and another n-bit input u2 and evaluate the function, so it can be even a black box function, we evaluate it and add the results modulo 2. Also, we component-wise add the two n-bit inputs u1 and u2. So that would be the same as bitwise XORing the two n-bit inputs, and evaluate the function on that input. The results should be the same. So this relation is really the textbook definition of linearity. So it's an alternative way to define linearity. Now, let's keep that in mind. And now think that we have a function with a large number of variables, and it's given possibly as a black box. And the question is this function linear or not? Of course, if the function was given in its algebraic normal form, then we could easily see whether it is linear or not. But it's not. It's given as a black box. If the number of variables was small, we could just query the black box with all the possible inputs and construct a truth table, and then we will be able to see if it's a linear function. But n is large, so the number of variables is large, so we can't compute the whole truth table. So what can we do if we want to decide, is this function linear or not? We use what's called the probabilistic linear test, which relies on what we've just seen above. So we pick n bits at random. So u1 is n bit vector. We pick another n bits at random and then test whether this relationship holds or not. So this is based on the textbook definition on nonlinearity. But in this context, it's often called the Bellare test because it was studied in this paper. So what do? We repeat this test many times. And if f passes the test all the times that we tried, then f is probably linear. We can't know for sure, but if it passed lots of tests, we think, all right, it's probably linear. If it fails at least some of the tests, then we know for sure that it is not linear. All right, so this probabilistic test tells us yes or no, a function is linear or not. So let's call, let's denote by P2 of f the probability of failing this test. So if a function is linear, it never fails the test. So in other words, the probability of failing the test is 0 for a linear function. So this is how these tests are used. Usually they are used just for deciding yes or no, is this function linear or not. But let's see if we can get a bit more information from this test. So if the function is not linear and it fails sometimes the test, it's natural to think, well, probably the more often it fails the test, the further it is from being linear. So we might expect that the probability of failing the test is proportional maybe to the distance between f and the linear functions. So this is not quite true, but there is indeed a relation between this probability of failing the test and the distance to linear functions. So there was a paper showing this lower and upper bounds of the probability in terms of distance to nonlinear function. So I'll show that on a graph. It's much easier to see. So on the x-axis, we have the distance of the functions to the linear functions. And on the y-axis is the probability of failing this linearity test. And it was shown that the probability is in this area. So we can only get points in this area. This is the lower bound and the upper bound, which means that for small values of the distance and the probability, there's quite a good correlation between the two. As we go further, the correlation is not so tight.
And there is a question in the chat. Yoga asked, how many trials are needed to prove this? Is this the same as Monte Carlo model?
I think it's in that style of Monte Carlo. I don't know how many trials we should do. I mean, depends on how accurate we want to be, how sure we need to be that the function is linear or not. Depends on the application, really. And yeah, maybe I might come back to it a bit later. But yes, okay. Thank you. So the simple answer is, well, it depends what we want to do with the test. Yeah. Was there another question? I see.
No.
Okay. Yeah.
That's the one. Yeah.
Yes. Okay. Oh, sorry, I didn't mean to do that. Yes. All right. So this was the test for linearity. Now, sorry. Yes. What we get here is the distance to linear functions. But if you remember, for our purposes, what we wanted to look at is the distance to affine functions, not to linear functions. So our idea was to tweak a bit this linearity test, sort of to repurpose them for our affinity, for the question of how close we are to an affine function rather than a linear function. And the main idea is, main observation is quite simple. A function is affine if it's either a linear function or a linear function plus one. So in other words, a function is affine if either f is linear or f minus 1 is linear, but here we are modulo 2, so f minus 1 or f plus 1 is the same. All right, so if we want to know whether f is affine, what we could do is check whether f is linear or f plus 1 is linear. So we ran the linearity test on f, and that will have a probability of failure of P2. And then we can also run the linearity test on f plus 1, but actually we don't even need to run it again, because one can check quite easily that the test fails on f plus 1 if it succeeds on f, and the other way around. So the probability of failure for of the test of f on f plus 1 equals 1 minus the probability of failure of f. So if we take the minimum of the two probabilities of P2 of the test failing on f and of f plus 1, and look at this minimum of the probability, we can see that f is affine if and only if the minimum is equal to 0. So either this probability is 0 or this probability is 0. All right, so that allows us to decide probabilistically, yes or no, is this function affine? But as before, we want to see if we can get a bit more information from the test. Is this quantity related to the distance of f to the affine function, so the nonlinearity of f? And our first result was to prove that indeed this probability, the minimum of the two probabilities, is lower bounded and upper bounded by some functions which depend on the nonlinearity. And the functions are very similar to the functions from the previous work that I've shown you. I'll show you again on a graph. So the graph looks the same, it's just sort of cut off here at 0.5. But there is another more important difference. On the axis, on the x-axis, here we have the distance to the closest affine function. Here we had the distance to the closest linear function. And remember, we are interested in the distance to the closest closest affine function. So we get this bound. So we can only get values within this area between the lower and upper bound. All right. Now there are other ways to check whether a function is affine. So these are known methods. We can go for 3 inputs, u1, u2, u3, and check whether f of u1 plus u2 plus u3 equals the sum of these values. So this is a test that can be used, it can also be used for checking whether a function is affine. Again, we pick some inputs, run this test, repeat the test many times. If the function always passes the test, then we say, yes, it is affine. We don't know for sure, but it is probably affine. If it fails for some, then we know for sure that f is not affine. Let's denote by P3 of f the probability of failing that test. And again, the question is, can we get a bit more information based on this probability? We know that probability is 0 if and only if the function is affine, but what about functions which are not affine? Does this probability tells us something about the distance to an affine function? So if it fails the test only a very small number of times, does it mean that the function is close to being affine? There is a lower bound for this probability, proved again by Bellare et al. So I will show their lower bound. That's the lower bound. Again, now on the x-axis, we have the distance to the closest affine function. There's also a generalization of this test proposed by Zhang and Zheng. What they do is they fix a number k, integer k, and then they pick k inputs and check whether this relationship holds. So you can see that the tests that we've seen before are the particular cases of k equals 2 and k equals 3. And we'll denote by pk the probability of failing this test. this probability is called, in the original paper, it's called the non-homomorphicity of the function. Now, when k is odd, f is affine if and only if the probability of failing the test is 0. So we can run this test for any fixed odd k and test whether the function is affine or not. If the function is not affine, does the probability give us some information about the nonlinearity? Well, in the original paper, they showed that there is a lower bound and an upper bound from this probability. I'll show them again on a graph. So this is the lower bound and this is the upper bound. So there's lots of room between the lower and upper bound. It's not very useful as it is. So our next contribution was to give much better lower and upper bounds for this probability. So there are bounds for the probability of failing the test, and they are expressed as functions of the distance of f to affine functions, so on nonlinearity. So let's see the graph. So this was the existing bound, and these are the bounds that we got. So you can see they are much tighter. The distance between the lower and upper bound is quite small. This is for k equals 5. For k equals 7, it's even smaller. You can hardly see that there's a lower and the upper bound. For k equals 3, this is our lower bound and upper bound. The lower bound is the same as the existing one here. All right. Now, we might ask ourselves, are this upper bound and lower bound tight? Well, we computed the exact values for a number of functions in small numbers of variables, because obviously you can only do exact values when the number of variables is low. So for many functions, we computed both the nonlinearity and the probability of failing the test. And this is the points that we got. So you can see that there are a few points which are on the lower bound. And actually, these are bent functions. They are on this branch of the lower bound. The bent functions will be here. On this branch of the lower bound are the functions which have just one monomial. But you can also see that a lot of the functions, almost all the functions, are actually very close to the upper bound. So the upper bound can't be reached actually, but there are lots of functions which are very close to the upper bound. Actually, most of them are close to the upper bound. Okay. So this is what I've just explained. And now we are ready to estimate the nonlinearity. So the general idea is that we run one of these tests. So for some fixed k, we run the affinity test several times, and we get a good estimation of the probability of failing the test. We see out of all the tests we've run, how many times the function failed out of all the number of tests we ran. And here, this is relevant to Rahul's question. So depends how much precision do we want to have for our estimation. And we will actually get an interval in which the probability, in which we think the probability is, with a certain level of confidence. All right, so that's what we do. First, we run the test and we get an estimate for the probability of failing the test. let's say we get it exactly. Of course, we don't get the exact value, we get an interval, but for simplicity, let's just say we've estimated this and got the exact value of the probability. Now, once we have the probability of failing, the second step is to use the lower bound and upper bound that we've just shown to get an estimate of the nonlinearity. So it will be more clear if we look at the graph. So let's say the probability is 0.3. That's what we got after running the test many times. We think the probability is 0.3. And that means that the nonlinearity, which is the x-axis, so if you look here at probability 0.3, it intersects the upper bound and lower bound. We will see that the nonlinearity must be between 0.102 and I computed that earlier, it's 0.107. So we get a very good estimate of what the nonlinearity is. If we have some higher probability, though, the estimate is no longer so good, but it's still we do get some estimate. So, for example, if the probability turns out to be 0.4, then the nonlinearity is between 0.1607 and here, okay, 0.281. All right, so that's the estimate we get for nonlinearity. It's actually, so when we are here in low values, we get quite a good estimate. When we get, we have a higher probability and higher nonlinearity, the estimate is not quite so good, but we still get a decent estimate. It's actually better to use, k equals 5. These are much closer. Around here, we don't have such a good situation, but around this area, we have a very good estimate. Same for k equals 7. The only problem comes around here. All right. So I've summarized in this table how precise the estimate is, but I won't go into too much detail. It suffices to say that when the probability is low, the estimates are pretty good. When the probability is higher, it's not as good. But the situation improves if we can use a higher k. So the test for k inputs with, for example, 5 inputs. We also look at the example I've shown before, the Trivium cipher. So you remember this function, we can't compute the nonlinearity, but let's see if we can estimate it. We did estimation with a variable number of iterations here, and the initialization vectors were set to all 0, so it's 80 variables. Okay, so if we have a smaller number of iterations, up to 80, so this is on the x-axis is the number of iterations, so we changed it from 1, 2, 3, and so on up to 1,000 and so. And on the y-axis, we have the probability of failure. I think the test was run 1,000 times, if I remember correctly. This was finally a project of one of my students. For the first 80 steps, the probability is 0, which is to be expected because most of the bits, nothing happens to them. And if we don't iterate the function too much, the output only contains bits which were shifted around, so nothing happened to them. So they are still a linear function or an affine function. After a while, we get this probability here. This is approximately 3/8 probability. And this again confirms what happens here. So a function like this, which has nonlinearity 1/4, one can also compute the probability of failure for such a function, and it is exactly 3/8. So after a while, one of the bits that was updated in this manner becomes the output of the cipher. And if we keep iterating that function up from around 96 iterations or so, it jumps to probability just under 0.5 of failing the test, and it stays at this level all the way through to 1152. And this suggests that it has reached a high nonlinearity, so nonlinearity close to 0.5. Which is not too surprising, because any strong cryptographic algorithm should achieve that sort of nonlinearity. But it's nice to be able to confirm that. So to summarize, we improved some of the existing bounds for the probability of failure of this type of affinity tests. We also proposed an affinity test based on the linearity test and gave bounds for the probability in that case. And then we developed a method of estimating the nonlinearity based on estimating the probability of failure of that test. And this estimation works quite well when the probability is low. When the probability starts to approach 0.5, it works less well. But in all cases, it also works better if k is a bit higher, so maybe not 3, maybe 5 or 7. All right, so this brings me to the end of my talk, and thank you for your attention. And if there are any further questions, please do ask.
Yeah, let's see. Any questions? Right, I have a question. From the presentation, you actually improved the bounds quite a lot. What's the secrets behind that?
Yes, I was a bit surprised that the existing bounds were so bad. Maybe they didn't think about it long enough.
Yeah.
Because so the techniques we used for those bounds, some of the techniques we used were actually the techniques that they used in this original paper. We did use some new techniques as well, but most of the techniques were already in the literature in some other contexts. So yeah, it was a bit surprising that the bounds here, the existing bounds, were so bad. Where this are much better. Yes. Mm-hmm.
Another question is, you suggest using larger k would be better. What is the cost of using larger k?
Yes, the cost of one test. So this is one test. Mm-hmm. For some of these black box functions, they are actually very time-consuming to estimate. So the function that we've shown, like the Trivium function, that doesn't take too long to estimate. So it's not much difference if we use a larger k or not. But for some other applications, one evaluation of a function takes quite a long time. So that's one reason why maybe we can't make k very big, but you know, k like 5 or 7 shouldn't be too big, but we shouldn't go too high with k because it just takes too long if each individual evaluation of a function takes quite a long time itself.
Okay. Yeah. Let's see. Any other questions from the audience?